Mohammed's with us. Let's see if anybody else is. Oh, yeah, we got a good crowd. We got Nicholas, William, Alex, Nathan, Reagan. Let's see who else is here. And Bryce, Brian, Taylor. Hope I didn't leave anybody out. Mohammed. We've got a good crowd. Yeah, excellent. Yeah. Hey, 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 hey. Okay, well, good. Yeah, we've got a good crowd. Now, what are we going to study today? Don't know. Let me see what we're doing today. And I'll get organized here. Today's the 29th. Not much of September left. 29th. Okay, now there's a homework number 12. Let me make a note of that. Homework number 12. That's 416 according to my schedule. 416. It's due Friday. That's due Friday. Where's my calendar? Let me get my calendar. That's due Friday, yeah. And then there's another one due Sunday. You don't need me to write that stuff. It's all in your schedule. But now what are we going to study today? Let's see, we started on mass flow rates, and I was working on a problem. I think it was 414. Let's go back over that. But I tell you what the topic is today, and it's control volumes. And the second law for control volumes. Not the second law. No, we haven't got to that yet. The first law for control volumes. That's the big topic. But let's go through this here, make sure we understand it. Unless you have a comment or question. If you have a comment or question, go ahead. Well, nobody's saying anything. Okay, well, let me find this 414 that I wanted to go over. I think I started on it. 414. Yeah, here we go. 0.6 meter diameter household fan takes air in at, this is 414. Let me give you the equations first of all. There's this one here. There's that one. And then there's this one here. Yeah, that's a nice one. And you can tell from this equation that you could write this like this. because m dot little v is equal to AV. Yeah, nice equation. Now, this is called mass flow rate. This is called volume flow rate. So there's some lovely equations for you. Now let's do our problem. Let's see, 414, 0.6 meter diameter fan takes air in at 98 kilopascal, 20 degrees Celsius. And delivers it. It comes in like that, but it goes out at 105 kilopascal and 20.4 degrees Celsius. And when it goes out, it has a velocity of 1.5 meters a second. They want to know the mass flow rate, inlet velocity, outcoming volume flow rate. We'll do all that. But first, what we're going to do is we're going to go P1 V1 equals RT1. And look here, we know the pressure, we know the temperature, we know it's air, so you can look up the gas constant for air, and we can get little v1. I'm going to shut up now, and you have 1 minute to get little v1 for me. On your mark, get set. On your mark, get set, go. How do I get rid of all these? Oh, I won't get rid of them. I'll just leave them there. Okay, here goes. V1 coming up. Well, I'll pick on one of my wonderful students here. William, unmute and say hi. Earth calling William.
Hello?
Yeah, hey William, have you figured out little v1 here?
Yes. I got a 0.859.
Good going. I got 0.85. I'll keep 4 digits here, William, just to be ornery there. Yay. Okay, now let's go P2 V2 equals RT2. And look here, we know P2. Yeah. We know P2, we know R, we know T2. And we're going to find little v2. Again, I'll shut up here for 45 seconds. See if you can get little v2. Go for
it. Professor, was our R value 0.28?
Yeah, thank you for asking.
And are we converting to Kelvin for this?
You must. The answer is yes. Otherwise, it doesn't work. Thank you for asking. Well, I got an answer. Did anybody, this might be wrong, but I'm capable of pushing the wrong numbers just like you guys are. Did anybody get 0.8024?
Yes.
Yes. I need another uh-huh.
Uh-huh.
Yay, good going. All right, well, we did great, but that's not what they wanted. They wanted MDOT. Now, here's the thing. See, MDOT coming in, incoming, is equal to MDOT going out. Put a little E there maybe for exiting. Or you could say 1 and 2 if you like. 1 and 2 is better than I's and E's. You see that mass flow rate is the same. We don't want more mass coming in than going out. The thing will explode. They've got to be the same. And they gave us the velocity going out. See, this is coming in, this is going out. So here's what we're going to do. We're going to go out, and that will get that, and it's equal to the area. What's the area? They gave us that. Isn't that the pi over 4.6 meters squared? Isn't that what they said? Read it. We're doing problem 414 right now. And they said, yeah, 0.6 meter diameter, that's it. And then the V, they gave us the V. It's 1.5 meters a second. And then what do? You divide by, see, if you're going out, these would be A2, V2, little V2, do you understand? So we got to go by 0.8024. Okay, we're going to get the mass flow rate. It'll be the same for going in or out. All right, here goes. Well, I get 0.5286 kilograms per second. Mass flow rate. Going in, going out, it's the same. So, ta-da, we just figured that out. Now, they want to know this here. But now, do they want going in or out? Let me read it. This is 414. Mass flow rate, inlet velocity. Inlet, well, we don't have the inlet velocity. We'll get it here in a minute. Outgoing volume flow rate. Ah, we can get that. Look here. We know MDOT. We know little V2. Little V2, yeah, we know that. No, wait a minute. I'm getting mixed up here. Just a minute. We want this. Looky here. We know MDOT. If you want this one here, put a 2 there. This is what I want to do. I don't need a 2 there because they're the same. Okay. Well, then we know the MDOT. It's 0.5286. So you multiply by V2. Here we go. I'm going to do that. I'm going to multiply by 0.5286. I just got the exiting volume flow rate. I'm getting 0.2794 cubic meters per second. There you have it. Now, what else do they want to know? Mass flow rate, we did that. Outgoing volume flow rate, we did that. Inlet velocity, we don't have the inlet velocity. Let's try this. M dot is equal to A1 V1 divided by little v1. Now we know this. And we know that. Yeah, we can get the inlet velocity, no problem. Here, let me write it here just a minute. I need some room here someplace. Now I know the m dot, it is 0.5286 kilograms per second. The area is pi over 4.6 meters squared. We're solving for the incoming velocity. And it's 0.85 cubic meters per kilogram. Okay, here's this lovely equation. We're going to solve for the velocity coming in. Go for it. Well, I did that, and I got the velocity, the inlet velocity. Just don't have any room to write it is my problem. Yeah, we'll make room. I did that, and I got the inlet velocity. Is 1.605 meters a second. What was the exit velocity? That was given in the problem, and that was 1.5. Well, and wait a minute, did I do those right? Yeah, I did those right. The air comes in at 1.6 and it goes out at 1.5. I thought it would get bigger, wouldn't you? Velocity of 1.5. Well, that's what it says. I guess we did it right. I'm kind of puzzled by that. I would think with a fan like that, that the exit velocity would be bigger than the inlet velocity, wouldn't you? Somebody explain that to me. Did anybody get the 1.605 when they did that?
Yes.
When they did that?
Yes.
That was a yeah?
Yeah.
Yeah.
Okay, well, I'm just kind of confused. I think we did everything right. Let me look. I got an answer book here. It just kind of bothers me that it comes in faster than. Yes, go ahead.
I'm getting a different answer for the volume flow rate.
For
This, yeah,
V2 dot?
yeah, I'm getting like 0.42 something,
Well, you
0.42.
might be right. Let's double check it. Let's double check it. Little v2, dang it, I erased all this stuff. Just a minute, let me find this problem. It's 414. I think I have the,
It looks like the answer you found is at the very top right corner of your board. 0.2794 meters, that one.
that's V2 dot. Okay. Okay, now here's what they say. They say the incoming velocity is 1.6. We got 1.605. So we agree with them. And what the exiting velocity was given, that's 1.5. So we agree with the book. We agree with the book. And now our exiting, that's this one here, isn't it? They didn't get that. I think Mohammed might be right. Let's do that together. I just need some room here. It's getting kind of messy. We're trying to find the exiting volume flow rate. Now M dot should be the same coming in and out. And they said it's 0.528. We said it's 0.5286. So we agree with the answer book on that. Now we just need V2. Now V2, they said is 0.8024. We got that. It's 0.8024. Only they got 80237. We rounded off. And now we're going to get the exiting volume flow rate. And Mohammed could get a thank you point for this. We'll see. 0.5286 times 0.80237. I don't know what this is, guys, but the answer should be 0.4241. Mohammed, is that what you got?
Yes, that's what I got.
Big thank you point for Mohammed. I must have pushed the wrong button. I hope nobody else has got confused. Was there anybody else that wanted to say anything about 414? It helps if you don't push the wrong button, that's for sure. Okay. Well, we kind of went over the mass flow rate and the volume flow rate, and hopefully we're pretty happy with that. And the topic right now is the first law of thermodynamics for control volume. So let me go through that with you. This is all in your book, but I'm going to try to explain it. It's I'll tell you where it is. It's chapter 4 someplace, right? Yeah. It's in chapter 4. It's on page, well, it's on page 116 for sure. So you guys could read that. Let me erase all this. We're going to talk about our first law for control volumes. And you could read it. It's on page 115. Page 115, 116. We have the first law for control masses that we've studied. And it's pretty easy. It goes like this. Now we didn't write little subscripts, control mass, control mass, control mass, control mass. We didn't write those subscripts on there because that's all we knew about was control masses. We had not studied control volumes. But let's suppose you had a control volume. Now it could be lots of things. It could be a turbine, for example, or a pipeline, or a heat exchanger, or 100 other things. But that's going to be the control volume. Now this is going to be before. We're going to do an after. Now here's your control volume after. Now the volume could actually change. It doesn't have to always stay the same. But there's your control volume. I put the control volume in black. Now here's the thing. We're going to have an incoming mass here. It hasn't come in yet. We'll just call that MI. There you go. We got some incoming mass there. And then later, what happens is that mass enters in to your control volume. There it is. It's entered in. And here maybe you can have an exiting mass. We'll call that ME. They could be different. Here, let me put some numbers in there so you'll understand. Suppose you had 12 kilograms in your control volume, and you had maybe, let's say you had 3 kilograms incoming mass, okay? And suppose you had those 3 kilograms come in, later they're inside your control volume, and suppose you had 2 kilograms that went out. They're no longer part of your control volume. They're in the environment. Well, I want you to notice that the total here is 15. And if 3 comes in and 2 goes out, that means you have, I think you have 13 inside here. Does that make sense? If you had 12 and 3 comes in, and 2 go out, you now have 13 in here. But here's the interesting thing. The 3 and the 12 add up to 15, and the 13 and 2 add up to 15. So you could put a boundary around this. We're going to put a red boundary around this. And inside that red boundary, we have the 15, the same 15 kilograms of matter before and after. We can treat that red boundary as a control mass. We'll put it in red. The control mass would obey this equation here. We're just going to write it out for this equation here. Now what this is the final total energy in our control mass. So that would be the, see if this makes sense. That would be the energy in your control volume at state 2 plus that exiting control mass plus its kinetic and potential energies. Well, those are specific. This whole thing here is your final total energy in your control mass. It's the energy in your control volume plus the energy of that exiting mass, because you have to include it. I don't know if that made any sense. Now here's your negative sign. We're just writing this equation. Now this one is the total energy in your control mass. That's the red outline now. And what that is you've got your original control volume energy, total energy, plus, see, we're doing this one now. Plus, you've got your incoming energy, a mass, times this here. These are your kinetic terms. These are your potential terms. And this whole thing is equal to, oh gee, I'm running out of space, dang it. It's equal to Q of your control mass minus the work of your control mass. All I've done is I've rewritten this equation for my control mass. But see, the control mass includes not only the energy in your control volume, that's the black outline, but it includes whatever energy you have in that. I should be pointing to this diagram. This is the final. The final energy is the energy you have in your control volume plus the energy that you have in your exiting mass. Then you subtract the total energy you have in your control mass, which is the red outline, and that's the total energy you have in your control volume, the black outline, plus the total energy that you have that are in your incoming mass. Look at it this way. If this doesn't make any sense to you, don't change your major, okay? We'll just, I want you to know where this came from. This is where it came from. You could read your book. That's another option. Okay, now what we're going to do is we made it that far. We're going to do some algebra. We're going to take this E2, the final total energy of your control volume, and we're going to subtract E1, the final total energy, no, the initial total energy in your control volume. And then we're going to put all the rest of the stuff on the right side of the equation. That's legal. So you have a QCM minus WCM plus, we're going to take, see, all this stuff is minus on this side of the equation, but it's going to be positive on this side of the equation. And then all this stuff here that's positive on this side of the equation, when you put it on that side of the equation, it's going to be like this. Okay, we're doing great. Wait a minute, I think I forgot something. Just a minute, let me stare at this. No, I don't think I forgot anything. Getting confused now. I don't want to get confused. That's not good. No, I think it's okay. Yeah. All right, now here's what I want to do. I want to get rid of this stuff about the control mass. It turns out that the heat transfer of your control mass is equal to the heat transfer of your control volume. So we can just substitute those. Now I'm lying to you a little bit because heat transfer depends on temperature difference between the system and the environment and the surface area across which that energy transfer takes place. But it's a reasonable assumption. We can substitute that. But when it comes to this here, this is a little bit different. That's equal to this. The work done by the control mass is equal to the work done by the control volume minus MI PI VI plus ME PE VE. You'll find that in your book. It's explained on page 116. I see it up at the top of 116. It's explained on 115. MPV, yeah, there it is. Yeah, these are explained on page 115. It might make sense to you that, see, the control mass, the control volume, you see this mass that comes in, it's doing work on the control volume. It's pushing in. And here, the control volume is doing work on the environment. It's pushing that mass out. That's where these terms come from. You have to subtract the work done on the body and add the work that the control volume does on the environment. And so what we're going to do is we're going to substitute all of that in here. Okay, it's ugly, guys. It's very ugly, but here's what you'll have. We want this equation. We're getting there. And if you'll just stay awake for just a little bit longer, we'll have this, and then we'll be able to use it. Now, this is a control volume equation, and that's what we want. And we're going to substitute. We're lying to you a little bit. We'll put a squiggle right there, but it's darn close. But when you subtract the work of the control mass, it's all of this business here. You have to subtract the work of the control volume minus MI PI VI plus ME PE VE.
Professor,
And we're not done yet. And then we have to add these. We've got the MI U of I plus KE of I plus PE of I minus, oh gee, I'm running out of room here, minus ME UE plus KE plus, ran out of room. We're almost done. 2 more lines and we'll have our equation. I hate to erase this pretty picture here. Let me erase this. I need the room really bad. Okay, now here's what we've got. This is all for control volumes now. Now here, can you see you got a minus and a minus that makes a plus? And you see that that's a plus. And then you have, see that minus there? You have a minus there, don't you? And so what you have here is MePeVe. See that minus? I'll write it this way. Now here's where I'm running out of room again, but there's these other two terms. There's the KEE and the PEE. Almost done, guys, almost done. And we'll have our first law for control volumes. Now, does anybody remember U plus PV and what that is? Let me pick on somebody. Taylor doesn't remember. Bryce, do you remember what U plus PV is, Bryce?
U plus PV.
Yeah.
Internal energy plus pressure times
volume. Well, it's specific volume and specific internal energy, but you could use big letters.
I don't think
That's okay. That's
do.
okay. How about my friend Nathan? Nathan, do you remember?
So sorry.
That's okay. Hey, look, we'll write it in big letters. Maybe that'll help. U is equal to P times V. Does not equal to. U plus PV is equal to something important that we've talked about.
Enthalpy?
Yeah, that's it. Who was that? Was that Mohammed? I don't know who that was.
Yes, it's Mohammed.
Yeah, Mohammed. That is equal to enthalpy. And here, this would be equal to specific enthalpy. Do you see that U plus PV and that U plus PV? Those are enthalpies. Those are enthalpies. So here, let me write this with the enthalpies in it. Here goes. We're almost there, guys. If you've just stayed with me this long, I'm proud of you, because it's pretty boring and tedious, but this is an important equation. And we're trying to write it for control volumes. This is final total energy minus the initial total energy of our control volume, which are things like throttles and nozzles and turbines and things like that. Okay, this is equal to the heat transfer to or from our control volume, the work done either on or by our control volume, plus MI. But see, that's an HI, isn't it? And what this little guy is the incoming specific kinetic energy. And what this is the incoming specific gravitational potential energy. Oh, gee, I'm running out of room again. But you see that U plus PV, that's an enthalpy, a specific enthalpy, plus your KE, plus your PE. Okay, I keep promising you we're almost done. We are almost done. What we're going to do now is we're going to divide by time. And we're going to make that time very small. Now, you studied calculus. That's the definition of a derivative. So I'm going to write it in here. I've shown you these diagrams. I'm going to write it in here. In fact, when you take that and you divide it by time, that's the definition of the derivative. Now we're talking about a controlled volume now. We're entering the exciting world of controlled volumes, like pipelines, for instance. See, when you divide by time, that's what you get. Now this one here is going to be, we'll put a dot over it. See, that dot represents the change, or not the change, the heat transfer per time. It's the heat transfer rate. That's the name of it. And this is W dot. Now that has a name. That's called power. Probably I should write that. This is the heat transfer rate. This one is power. What it is it's work per time. Well, that's what power is. It's work per time. Plus MI HI plus, why don't we just write it as, see, kinetic energy is 1/2 mv squared, right? So you just have VI squared over 2. And potential energy is mgh. So you just have G, only they don't use H because H is used for enthalpy. They use Z. So you see you've got mgz or mgh, that's gravitational potential energy, and 1/2 mv squared, well, that's kinetic energy, minus, don't forget the dot now if we're dividing by time, HE plus VE squared over 2 plus GZ. See, they use Z for height rather than H for height, because they use H for enthalpy. And yay, we're done. We finally got it. I don't know if that made a lick of sense to anybody, but we did show you where it came from. You could read your book. It's the pages 115, 116. And we now have our first law. This is it. This is our first law for controlled volumes. But I'm pretty lazy and I'm going to quit writing control volume down there. We know it's for control volumes. When I write this, I just go dE dt equals Q dot minus W dot plus M dot coming in, HI plus VI squared over 2 plus GZI plus M dot E, HE. I'm so lazy, a lot of times I'll just go dot, 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 because you know what's coming. Now here's the thing. Sometimes you might have to worry about a summation sign in here. There might be, like you might have a turbine that has 2 inlets. It's possible. You could have 2 inlets, or you could have 2 exits. See, if you had 2 exits, then you'd want to put a summation sign in there. And in fact, it's possible you could have summation signs here. You could have heat transfers in two different areas with two different boundary temperatures. But we'll do simple problems at first. But I just want to warn you that it's possible that you could have summation signs in those. Well, there you have it. We have our first law. Now let's use it to solve some problems, shall we? Now, one of the beginning problems is a nozzle. And there's a nozzle problem I'd like to work in your book. This is an example. It's on page 120. No, 121. Let me make some room. We have our equation now. I'll leave this. I need to leave one of these up here. I guess we could leave that one. And we're going to do a nozzle. Now there's a lot of different devices, but a nozzle is a thing kind of like this. You have stuff coming in and stuff going out. Now coming in, you got m dot, but you got the same m dot going out. I don't know if that shows up on your screen or not. But in this problem here, this is on page 121. We're going to do this example. Now I am not going to peek and see how they did it. I want to see if I can do this example in your book on page 121. It's example 4.4. It's example 4.4. They said steam at 0.6, let me write this down. Steam at 0.6 megapascals and 200 C enters a insulated nozzle with a velocity of 50 meters a second. It leaves at a pressure of 0.15. Wait, you see, it comes in at 0.6 megapascals. I don't know if that's showing up on your screen. And 200 Celsius with a velocity of 50 meters a second. That's where it comes in at. And then it goes out. Let me read this. It leaves at a pressure of 0.15 megapascals, velocity of 600. By the way, that's the whole purpose of nozzles, is to speed up. See, it came in at 50 meters a second. It goes out at 600 meters a second. That's what nozzles do. They increase the velocity. Well, I think that's all the information. They want to know the final temperature. So this is our device sketch. And this is our incoming. And then we have a process that takes place here. It's actually an adiabatic process because there's no heat transfer. They said so, it's insulated. And it leaves at 0.15 megapascal with a velocity of 600 meters a second. Okay. Now we're going to do our PV diagram like we always do. But first we're going to write the first law for nozzles. Now this term here is going to be 0 because this nozzle is what they call a steady state device. This temperature doesn't change. This nozzle is just running for hours. It comes in at 600 and it stays at 600 coming in. And so the change in total energy inside your nozzle doesn't change any with time. Now the temperature changes with location. See, it goes out at a lower temperature. I don't know what it is. We're going to find it though. But see, T1 is 200. Going out, it's going to be colder. Steady state devices don't change any of their properties with time. They sound the same. They make sort of a roaring sound. An hour later, it's the same roaring sound. The pressure coming in is 0.6. Believe it or not, the pressure goes down. It does not go up, it goes down. The velocity goes up, but the pressure goes down. I'll explain that someday.
Was it mentioned in the problem that it's a steady state device?
You just have to know that it's a steady state device and that none of the properties change with time. But thank you for asking. So this is 0. This is 0 because there's no heat transfer. It's insulated. This is 0. See, nozzles are pretty simple. It doesn't do any work. There's no little turbine blades spinning or anything like that. So what you have left is your M dot. Now you don't need an I and an E. It's just a plain old M dot. They're both the same. Whatever's coming in is going out. And what you have is, call it H1 plus V1 squared over 2. This nozzle is not going up or down, so you don't even need to worry about your gravitational potential energy per mass. Just forget it. And so here's your first law for your nozzle. Since the M dots are the same, you can write the equation for a nozzle like this. In fact, this is the first law for a nozzle. You'll see that equation on page 121. They've written it. This is your nozzle equation. That is your first law, control volume equation for a nozzle. There you have it. Now to solve it, they give you the incoming temperature and pressure, so you can get this H. Let's just go to our table. Help me find, I need to draw my PV diagram, but help me find steam back in the back here at, well, it'd be 600 kilopascals, wouldn't it? So shop around. It's in superheated vapor, but we probably should draw that PV diagram. Find 600 kilopascals and 200 Celsius. I found it. The specific enthalpy at 600 kilopascals, 200 Celsius. This number right here, I need this room. This number right here is 2850.12 kilojoules per kilogram. Now I'm going to wait till I hear a couple of ahas that you found that. Now there's one. It's 0.6 megapascals, that's 600 kilopascals, and 200 Celsius. Go to the back for water and find 285012. I need another uh-huh.
Uh-huh.
Yeah, there's one. Good going. Now, they gave you the incoming 50 meters a second. You have to divide by 2. Hey, look, we know all of that stuff. Equals. Now, we don't have H2. We're going to find it here in a minute. But they gave you the exiting. It's 600 meters a second squared divided by 2. We have an equation here with only one unknown. See it? Isn't that nice? There's only one unknown. And that's H2. And with that H2, we can get the exit temperature. They wanted to know what that was. We're going to find the exit temperature for this nozzle. They cool off. They always do. But now here's the problem. If you look at these units, these are meters squared per second squared. These are kilojoules per kilogram. It turns out, and you can prove this, that a meter squared per second squared is equal to a joule per kilogram. We don't want joules per kilogram, we want kilojoules per kilogram. So to get kilojoules per kilogram, you have to do a little trick. You have to multiply this by a kilo and divide by 1,000. And you have to do the same thing here. You have to multiply this by a kilo and divide by 1,000. Okay, now we have a lovely equation and we can find the exiting specific enthalpy. I'm going to shut up. You've got a minute. I want you to find the exiting specific enthalpy for me. Go for it. Well, I found the exiting specific enthalpy. How about you?
Yes.
What'd you get?
I got 2,671.37 kilojoules.
That's what I got. That's what I got. 26. We'll just round it off. 2671 kilojoules per kilogram. Now we're going to get the temperature. I need some room to do that. Or I could just tell you how they do it. See what we're doing in case somebody kind of woke up from a daydream. We're doing example 4.4. It's in your book. It's example 4.4. It's a nozzle. It's on page 121. Now, what we found out, we think we have the exiting specific enthalpy, and also we know the exiting pressure. The exiting pressure is 150 kilopascals. We can get the exiting temperature from the tables. It's steam, it's H2O. Go to the tables. Well, better yet, let's just look and see what they said. Hey, you know what? They agree with us. They say that the exiting specific enthalpy is 2671.4. That's what we got. We did good. Then here's where we would really need the PV diagram. So we're going to make one. Here goes. Oh, gee, never have enough time for this stuff. But we're going to make a PV diagram now. Now, they didn't do that. The book didn't do that. They solved this problem, but when you do problems for me, what happens if you don't do a PV diagram? So something bad happens.
I think you get expelled, right?
Do it. Okay, now let's find what we got. Now we're coming in at 600 kilopascals. Go back here and find water in the tables. All right, I found water. Now, 600 kilopascals, man, that's way down low, you know what? 600, that's pretty low.
Which table, I'm sorry, are you looking at specifically?
Water. They said steam. So we need water. Now, there's an isotherm going through here like so. At 600 kilopascals. That isotherm happens to be a 158.85 degrees Celsius. And that is at 600. Is this showing up on your? Can you guys see? Can you guys see what I'm writing?
Yes.
Yeah, good. That's 600 kilopascals. Let me do it over here. I can't. Let me start over again. I need this thing where I can see it for sure. There we go. Now we got 200, we got 600 kilopascals. And the temperature there at 600 kilopascals is 158.85 degrees Celsius. And the pressure is, see, I can see that now. The pressure is 600 kilopascals. And we're at 200 Celsius. Well, see, 200 Celsius, probably need to draw this a little better. See, 200 Celsius is up here. Come over here. This is 200 Celsius. And so we know we're at 600 kilopascals and 200 Celsius. That puts us right here. State 1. We're in a superheated vapor. We did good. And that's where we looked this up at. I think we looked that up. That's where we got it from, the superheated vapor table. But now H2 is 2671. And it's at 150 kilopascals. Well, we're going to have to do that. That's down here someplace. 150 kilopascals. We know we're on this 150 kilopascals spot. Yeah, let me kind of fake this a little bit. There we go. Now what happens is we come down in here. I have to keep adjusting this thing. Those are a little closer together. There we go. We know we're right here. And we're going to go to here. This is state 1. This is state 2. It turns out that the enthalpy, our exiting enthalpy, is smaller than this Hg, little hg. See, at 150 kilopascals, the little hg is 150 kilopascals. It's 2693.54. That's 2693.54 at 150 kilopascals. Well, our value is 2671 kilojoules per kilogram. Kilojoules per kilogram. You know what? We're inside the vapor dome. And if you read the problem, they're inside the vapor dome. And they came up with a quality of, an exiting quality of 0.99. I'm on page 121. You can read it. Hey, look at where we are at state 2. There we are. And I can tell you the temperature there at 150 kilopascals, we can just look it up. See, we're talking about this temperature here at 150 kilopascals. This temperature is, help me find it, at 150 kilopascals. I got lost again. There it is. It's 111.37. This temperature is 111.37 degrees Celsius. You should be able to find that in your H2O tables for 150 kilopascals. That should be the exiting temperature. Now, what do they say it is? They said the exiting temperature is, I don't know, where do they have the exiting temperature? They ever say it? I thought we were supposed to find the final temperature. Yeah, they asked us to find it, but I don't see where they ever did.
It's almost like they worded it to either find the final temperature or the
or the quality. Okay, I understand. Thank you for mentioning that. Well, there's the quality. You can see that it's dang close to the saturated vapor line, but you do have a final temperature. The final temperature is the 111.37 Celsius. So you came in at 200 Celsius and it cools off to 111 something Celsius. So yeah, it's a matter of semantics or what they're asking for. Well, we try to give you a lot of stuff here today. Have fun doing that homework, and this will all make better sense to you by and by, I hope. Any last comments or questions before?
Yeah, I have a question about the tables. If I could just like hang out and share my screen with you after everybody leaves.
Yeah, I'll stay for a while. Go ahead. I'm
Thank
listening.
you.
I won't cut anybody off. We'll just stay for a few minutes.
Okay, let me figure out how to do this real quick.
Yeah. Now, who was I talking to?
This is Taylor.
Taylor? Okay, Taylor. Yeah, this is just class is officially over, but I haven't signed off yet because Taylor wants to ask something.
Yeah, it's about the tables. I feel like mine might have the temperatures. You said that at 150 kilopascals, the tables read 111.37. Is that right?
That's right. Let me see if I can find that, Taylor.
And I just want to
100?
verify that's table B.1.2.
It's table B.1.2, exactly. And that's the temperature.
Are you using the
111.2.
online book?
Yes, I am.
Okay, I ran into this problem too. The temperature and the pressure are flipped on
They've,
B.1.2.
yeah. Those-
I thought I was
They
going
flip.
crazy. So that's true.
I
It's
thought
flipped?
I was too when I ran into it earlier in the
Yeah.
class. I was like, man, I am just not reading this right.
They flipped them.
Okay, well
They-
that
they-
helps a lot. And is it just that table, or you know if there's other mistakes like that?
I've just noticed that one. All the other ones seem to be in order.
Yeah, I hate to say definitely, but I think I told the class this a while back, but I might not have. I don't remember.
I may have
Yeah,
just missed that.
They've got the right numbers. It's just that at the top, their label is backwards. But thank you for mentioning that. You helped a lot of others, I'm sure.
Yeah, that
But-
was really driving me crazy. So for B.1.2, they have it's supposed to be referenced
Supposed to
by
be-
pressure only, and then the temperature is
Yeah,
the
it's supposed to be
75.
pressure in kilopascals, and then the next column is temperature in degrees Celsius.
Okay, thank you so much. That helps a lot.
Yeah, that'll drive you crazy. Well, anybody else? Well, I'm so
Thanks
glad.
again.
Yeah, I'm glad you spoke up. Okay, guys, ta-ta for now. I will see you Thursday at 11, right?
Yes, sir. Thank you very much.
Yeah, thank you very much. See you then.
Thank you.